Hello everyone, welcome to Dakshana e-classroom program. So in last lecture we started viscosity or elasticity and viscosity, a new chapter. Here we saw that how basically at atomic level the elasticity matter and how we can understand. So at atomic level we can understand that two atoms are bonded and the bond actually act like an spring. So because of that there is flexibility and there is possibility. Now depending on how exactly in different solids atoms are arranged, if like crystalline solid we are talking about, then the atomic arrangement is a in proper and regular manner, like BCC, FCC and different types of arrangement. So there when we are applying some external force that we call deforming force, it try to change the separation between them, and so because the bond is acting like a spring, some restoring force get developed between two atoms that try to restore the equilibrium position or try to bring back the solid material back to its original configuration. So that's why some solid have the property, have the capability to restore their original shape and size because of the restoring force developed between the atoms when external deforming force is removed. Deforming force which try to means which is applied externally and which try to change the shape and size of solid. So that is what we discussed, and we saw some definition that stress. So stress we discussed, there are basically three type of stress. One is longitudinal stress. Longitudinal stress further can be like two type, either it's tensile when it's creating tension in the solid, or it can be compressive which try to basically reduce the size, you can say, or which create compression in the solid. So it can be like both are when it's like applied along the length or normal to the surface area of cross section, then we call that as longitudinal stress. Similarly, another is bulk stress, or we call that pressure stress. So when stress or a force is acting from all sides on the solid body normal to its surface, that also result in some deformation in the body, and we call that bulk stress. So that actually normally act when some body is placed either in some fluid or maybe either some gaseous pressure. So most of the time it comes out that bulk stress is simply equal to the pressure applied on the body. And similarly there comes another, that is shear stress. Shear stress, so sometimes what happen actually, if we are having this is a solid block, so then this is, let's say it's normal surface, then instead of applying this way normal force, we apply force along this surface. So like stack of books, you can apply press the by those block of books actually, or either one block you can press this way, or you can pull it this way, or sometime we apply force on the upper surface in this direction and lower surface in this direction, so like this way. So on this surface force is applied tangential, and this is also called shear force, and the stress developed due to this force is termed as shear stress. So that is what we discussed up to last class. We saw a few applications, we saw simple applications, simple problems based on it, that how we can calculate bulk stress, shear stress and longitudinal stress. So now the point is that all these stress, what they are trying to do, they are trying to create deformation in the solid body or in the specimen. So when some deforming force is applied, that ultimately creates some deformation in the body, and we try to measure that deformation. For that we define a new quantity, and that is termed as strain. So strain is sort of like a measurement of deformation created in the body by deforming force. So it's the measurement of deformation created in the solid body by deforming force, and it's denoted by epsilon. This is read as epsilon, and this is equal to change in configuration. It is the ratio of change in configuration of solid body divided by original configuration. This is defined as strain, and you can see it actually here. Whatever the dimension is here, numerator, same dimension is for denominator. So that's why strain, it is a dimensionless quantity and also no unit. Strain doesn't have any unit. Now, because there are three type of stress, so they create different types of deformation. So that's why we measure them in different ways, and for that we need to define three types of strain also. So one again corresponding to longitudinal stress, or you can say the deformation created by longitudinal stress. We measure that, or we define that longitudinal strain. Is it so? Longitudinal strain. Longitudinal strain, what happened actually here, the simplest case here, see, so let's say this is one rod, is it, a cylindrical rod on which some force is applied, which is trying to deform it, and it has some original length. Let's say original length, it's L0 is the original length. So once this deforming force, what it trying to do, it's trying to expand it, it's trying to increase its length. So because of this force, after some time its length will change and it will increase. So let's say it has expanded this way, is it, so the length of this rod has changed, and this length, this is some L0 plus delta L. You can imagine easily. So this was the original length. Once this deforming force, and you can understand if its area of cross section is A, then force divided by A, we will define that as stress. So this stress is trying to increase its length, that is changing its configuration. So longitudinal stress, is it, changes the configuration of the solid body, and here tensile stress is increasing its length. So the change in length, what is the change in configuration? This change in configuration means change in length divided by original length, that is defined as longitudinal strain. So it is created, or you can write it is the effect, result of, it is the result of longitudinal stress. It is the effect of longitudinal stress, and this is defined by, it is equal to epsilon longitudinal, that is equal to change in length divided by original length, and this is called strain or longitudinal strain. So what it will be, if I just write it for this example, then it's equal to delta L divided by L naught. This is the longitudinal strain. So similarly we can define different type, like bulk stress, bulk strain, that is basically, and shear strain also. So next is bulk strain. Exactly in same manner, it is also, or I can write it is the result of bulk stress or pressure stress. So in this situation, what happened, like this is some rigid body on which bulk stress is being applied. So this, and bulk stress will be simply equal to what, pressure. Because of that, so it is having some, due to bulk stress, what happen actually, what changes normally happen, that is actually the change in volume, is it. So bulk stress, it result in change in volume, of solid body R, right? So if V naught is the its original volume, let's say before bulk stress is being applied, V naught it's the original or initial, you can write volume, and after that, let's say this is the deformed shape of the body, and this is V final, and I will write V initial minus V final is the delta V. So this is the change in its configuration. Then I will define the volumetric strain is defined as delta V divided by V naught. This is termed as change in volume divided by original volume, that is equal to change in volume divided by original volume, and this is termed as volumetric strain. So definitely you must be understanding here also, it's simple thing like change in volume, that will be also a volume dimensionally or like unit wise, and this is also volume, so unit gets cancelled, so it's like unitless and dimensionless quantity. And there comes the third one, that is called shear strain. Let me just erase this space for that. So shear strain is the result of shear stress. Shear stress also created some deformation, and we call that as shear strain. So you are already clear with shear stress, what exactly it is. Here deformation is a little bit different. So here let's say this is the front view, is it, of a solid or I will say a block. For your understanding purpose, let me draw it a little bit 3D in this manner. So here what happens actually when shear stress is applied, so this is the force and this is the force, tangential force that is actually applied and creating shear stress. So shear stress area is, this is the area. Now what happened actually here, so if I take this is its length, then because of this stress the deformation will be something like this. Let me draw that deformation. Okay, so because of this shear stress, the deformed shape of this body will be something like that, because this force is applied in this manner. This, so with respect to this, the top surface will move forward slightly, and that we believe that this red mark will be the final shape after deformation. So in this situation, the deformation is something different from this and this. And here, how we define the like shear strain? What is that like? So first thing is, it is the result of shear stress, right? And here, so if I let's say measure, this is angle theta, and this change in this shift is, let's say, delta x, right? Remember that this length is original L, and correspondingly this how much length has shifted, this corner has shifted by some amount delta x. Then here shear strain is defined as shear strain, this is defined as delta x divided by L. Just try to remember it, try to remember this expression, because its definition is little bit different. It's not the way it's like change here. This change is coming, so you will not be taking this length, it's basically this length divided by this length is defined as shear strain. So you can see this is also equal to, like I can write shear strain is equal to what, tan theta, that is equal to delta x by L. And sometime, is it, or you can write as, or I will write either, you can take for small theta, because most of the time this theta is actually small, so you can write for small angle, we can write tan theta is equal to what, simply theta. So in that situation your epsilon is equal to theta equal to or equal to delta x by L. So this is your shear strain, right? So I hope you must be clear, and all like strains are dimensionless, unitless quantity. Simple things are there. I don't think there is any confusion like anybody should have like about it. It's straightforward. Some changes are happening because we are trying to deform the body by deforming force. we are applying deforming force in different manners, so that result in deformation of body in different ways, and we are trying to measure that deformation in a quantity that is termed as strain, and it's measuring the change in original configuration divided by original configuration, that is defined as your shear strain, like strain. So we have like longitudinal stress, corresponding to that we have longitudinal strain, bulk stress, corresponding to that we have bulk strain, and shear stress, corresponding to that we have shear strain. So just remember these relations. Let's see more. Okay, so we understood stress and strain, and we saw that actually strain also like somehow depends on stress, is it? Because when we are applying stress, that then the result is the strain. So Hooke's law, actually it's sort of like, you can say it's the relation between stress and strain, and it tells, so what is exactly Hooke's law? It states that within the elastic limit. Now what is elastic limit? Just wait, I will define it. So within the elastic limit, stress is directly proportional to strain. This is termed as Hooke's law. So stress is directly proportional to strain. I can say sigma directly proportional to epsilon, and I can write sigma. This proportionality constant is replaced by E epsilon, and this E is sigma upon epsilon. This is stress divided by strain. This is called modulus of elasticity. So modulus of elasticity is the ratio of stress by strain, and you know the dimension of stress is what? Newton per meter square or Pascal. Strain is dimensionless, so I can say E is also having same dimension or same unit of you can write E, so modulus of elasticity, that is basically E. So its unit first is same as of stress, that is Newton meter square or Pascal, right? As strain is dimensionless, unitless, so that, and first thing is simple, this relation stress is directly proportional to strain within elastic limit. This is termed as Hooke's law, and we can write it this way. So E is the ratio of stress divided by strain, and this is the proportionality constant. This we define as modulus of elasticity. Unit is simply this. What about modulus of elasticity? Modulus of elasticity depends on the material of solid body. It depends on the material, means nature of material. It's like made of which metal, which like material exactly, and it's independent of dimension of body. Means if you are changing, if you are, let's say, taking one rod, and it's, if you are taking another rod of double length, then like this, modulus of elasticity of that rod is not going to change until you are not changing the material, is it? So, and another point, it depends on the temperature also. This is about modulus of elasticity, and within the elastic limit, this sigma, this is actually that. So you can write the slope of stress strain curve within elastic limit is E. Then we will see next basically because stress and strain are also of three types, right? We have seen longitudinal stress, longitudinal strain, bulk strain, shear stress, shear strain. So based on that, we define three types of modulus of elasticity. So by this time, you should be like clear with this Hooke's law, what it simply tells, and what is modulus of elasticity, on what factor it exactly depends. So let's see three different types of modulus of elasticity. Okay, so type of modulus of elasticity. So there are three types of modulus of elasticity. One is for longitudinal stress and longitudinal strain, that is called Young's modulus, or you can say Young's modulus of elasticity. Another, when bulk stress and bulk strain, then it's called bulk modulus. Of elasticity, also you can write it. And third one is when shear stress and shear strain is there, then we define it's not shear modulus, it's called modulus of rigidity. So let me talk one by one. First is Young's modulus. Right? So when longitudinal stress is applied, then the ratio of longitudinal stress to longitudinal strain is strain within the elastic limit. Wait for it, I will clear it what is exactly elastic limit. So that is termed as, so Young's modulus can be written as stress longitudinal divided by strain longitudinal. And what is stress longitudinal? It's force divided by area. What is strain? That is delta L by L. So it comes out to be F into L divided by A multiplied by delta L. This is called Young's modulus, or Young's modulus of elasticity. So you can just consider one simple case. Let's say we have one rod of length L and some weight m g is hanging on it. Change in length is delta L, right? Then we can write for this case the Young's modulus is y is equal to force is divided by area into L divided by delta L, that is equal to mgl. Area A and change in length is delta L. So this is the Young's modulus, right, of elasticity. So here if we can write delta L, if let's say length of rod is doubled, right, then what I can write, epsilon is equal to what, change in length 2L minus L divided by original length L, that's equal to simply 1. Then Young's modulus is equal to what, stress upon strain, and strain is equal to 1, so this is equal to simply stress. So I can write Young's modulus is also equal to the longitudinal stress when the length of wire is double. Young's modulus is equal to longitudinal stress which double the length of wire or rod. So this is a Young's modulus, and that is simply longitudinal stress divided by longitudinal strain. Next is bulk modulus. Okay, next is bulk stress. So bulk stress, when a body or solid, basically here it can be even fluid, means liquid and gas also sometime, when it is subjected. So when a solid and fluid can be liquid and gas also, is subjected to uniform pressure that result in change in volume of solid, or I will write fluid. So this ratio of bulk stress divided by bulk strain is termed as bulk modulus. It's denoted by letter K. Bulk modulus is denoted by K, or sometimes it is also denoted by capital B. Is it? So K is equal to what? So let's say this is some body, when it is subjected to bulk stress will be equal to what? It's pressure. We write it, bulk stress is equal to what? Simply pressure. So when it's subjected, then its volume changes, and let's say this is the initial volume, this is the final volume. So we can write delta V is equal to, and here normally what we write is V final minus V initial. So when it is like subjected to compression or pressure, always what will happen? Volume will decrease actually. So delta V, we normally write V final minus V initial. So you can definitely see delta V will be what? Negative. Is it? So here strain will be always negative. So that's why we use, to make the quantity positive, we use one more negative sign. So it's pressure divided by strain, that is delta V by V. Here this negative sign, because negative compressibility doesn't make any sense. Negative bulk modulus is not making any sense. So this negative is not making this quantity negative. It's because this delta V will be always negative. So to make this quantity positive, we are using here negative sign. Negative sign here simply saying negative sign is implying the volume is compressed or decreasing. Is it? So whenever bulk stress is applied, pressure stress, so simply this ratio is termed as bulk modulus. That can be also like so bulk modulus, that is K is equal to, sometimes like we write P as sometimes change in pressure also. Remember that many times it is like you can write it absolutely pressure, or otherwise let's say initially there will be something like some pressure, some stress will be there when some initial shape is there, then some additional load, additional pressure is applied, then many times we express this delta P in terms of delta P. So remember that. So let me write it actually. So many times this P is replaced by change in pressure. In pressure means delta P. So remember that actually. So in that case, K is equal to what? I can write delta P divided by minus of delta V by V, that is equal to minus delta P into V divided by delta V. This is termed as bulk modulus. Bulk modulus. Here we define one more quantity, that is called compressibility. It is the reciprocal of bulk modulus, that is termed as compressibility. So bulk modulus, it's defined for like say solid or fluid. Fluid means like it can be gas and liquid also. So for that we can define there is also compressibility, how much compressible it is. So compressibility, it's C, it's equal to 1 by K, and that will be equal to mathematically delta V divided by minus of V into delta P. This minus you can use here also. So this is called compressibility, right? Higher the compressibility means like by applying the higher, the means like change in volume is higher, right? So that what it mean actually, higher the V means for applying same pressure, let's say we are considering same volume, same pressure is applied, so higher compression it can be compressed more, is it? So that's like a high value of C means it's more compressible and vice versa. And remember that it's inversely proportional, then I can say if bulk modulus is high means it will be less compressible. So solids normally have higher bulk modulus, is it? So high bulk modulus, high K implies less compressibility or less compressible, right? So this is about bulk modulus, and last one is modulus of rigidity. Okay, next is modulus of rigidity. So again, this is also whenever like some solid body is subjected to shear stress or shear force, then I can write within the elastic limit, that is like must. So within the elastic limit, the ratio of shear stress to shear strain is defined as, you can write bulk modulus of rigidity, and it's denoted by a letter that is termed as, that is called as eta. So modulus of rigidity, it's denoted by letter eta, so that you can easily understand. So let's say this is the initial shape and force, shear force is applied. Because of that, the result is this: the body gets deformed in this manner. Let's say this is the deformed shape, and here if I'm taking, this is theta. So how we define this is delta x, and this is, let's say, L. Then shear strain epsilon here, that comes out to be equal to theta equal to delta x divided by L. This is shear strain, right? And shear stress, we can write it's tau, that is equal to force divided by area. If this is the force in area of this surface on which force is applied, that force divided by area is shear strain. Then we can write modulus of elasticity, modulus of rigidity is equal to tau divided by epsilon. This is force divided by, this is what, shear force or tangential force divided by area, and this is equal to, you can write either theta directly or either delta x by L. So this is called modulus of rigidity. So these are three different types of modulus of elasticity. Modulus, first is Young's modulus, that is defined for longitudinal stress and longitudinal strain. The ratio of longitudinal stress by longitudinal strain is termed as Young's modulus. Next one is bulk modulus, bulk stress, that is basically pressure divided by bulk strain. And the last one is modulus of rigidity, that is shear stress divided by shear strain. Let's see some applications, some problems. So here, like, problems are not much complex here. We will see, we will solve, like, you just need to remember the terms, you need to remember the formula. Things are very much simple here. You will be asked problems, so like one few terms, few quantities will be provided to you, the next one you will be asked. So here, like, see here, if eta is given to you, maybe like this is like theta is given, this is given, then how much force will be required to create that much deformation, that much like shear, is it? So something like that, and let's see, then everything will be in front of you. So let's solve some problem based on it. Okay, let's see some application based on the concept that we just have studied. So here we have simple problem: a 5 meter long wire and area of cross section this, so this is the length 5 meter, area of cross section minus 10⁻⁻⁴ meter square is fixed at one end. So this, let's say a wire which is fixed at one end, its length is given as 5 meter, area of cross section is given as 10⁻⁴ meter square, and 1200 kg weight is hung on this. So here 1200 kg weight is hung from other end. Find the elongation of wire. Young's modulus of this wire is also given. So it's like simple formula based. So what we have known is Y is equal to force into length divided by delta L. Now see, you can see Y is given force, that is equal to the weight of this mass, and length it's given area of cross section. So it's simple straightforward formula based problem. We can simply substitute here. So Y is coming out to be force into L divided by area multiplied by Young's modulus, and force is what, 1200 multiplied by 9.8, length is 5 meter divided by mg is the force, that is equal to weight. Area is 10 power minus 4. In Young's modulus is 0.98 into 10 raised to power 11. Right, this is, so now we can simply, this 98, this is 10, right, and 10 raised to power minus 4, so it will be like simply 5, and then taking it up. So delta L is coming out to be this 12 into 5, so it's 6 and 40 multiplied by 10 raised to power minus 5 meter, and this is gone, so it's basically 0.6 meter. This is the elongation of wire. So there is nothing much complex, it's simple straightforward formula based problem. Everything is provided, length, area of cross section, this weight is creating the stress in this wire, and Young's modulus is given. We know the formula, so just remember this formula, substituting, rearranging, and we are getting the answer. Let's see the next problem. So what force is required to stretch a copper wire of this area in cross section to double its length? Is it? So means the length of the wire is supposed to be double. So let's calculate. So that what it implies, length, let's say initial length Li is equal to L, then final length is equal to what, 2L. So what is the strain? Strain is equal to delta L, that is 2L minus L divided by L, that comes out to be simply 1. And it's talking about what force. So force we can write, first thing is Y is equal to force divided by area into strain. This is stress divided by strain, and strain is equal to simply 1. So force is equal to what? Force is equal to this Y multiplied by area, and Y is given as 1.3 into 10 to the power 11 multiplied by area is 1 centimeter square, that can be expressed as 1 into 10 to the power minus 4 in meter. So this comes out to be, the force is equal to solving 1.3 into 10 to the power, this is a 7 Newton. This is the answer to problem. Right, okay, let's see next problem, little bit just lengthy compared to these two. So steel wire of length 4.6 meter and cross sectional area this. So here two wires are given, stretches by same amount as a copper wire of length 4 meter and cross sectional area 4.0 into 10 to the power minus 5 meter square under same load. So remember that here we need to, delta L is same for two wire, and we have steel and another is copper. For steel, length is 4.6 meter, area of cross section is 3 into 10 to the power minus 5. Here length is 4 meter, it's 4 into 10 to the power minus 5 meter square area of cross section, and same stress, and like the extension is same and load is also same, means force is same. That's the information under same load. Find ratio of Young's modulus. So just like we need to use the information given to us in the problem, and then we will get some expression, and substituting the value we will get answer here. So let's see it here. So this is all information given to us, and this delta L. So first we know actually Young's modulus is equal to what? Force divided by area into delta L multiplied by L, right? So rearranging it, because we are provided force and delta L is same, so delta L can be written as, and delta L is equal to what? Force into L divided by area into Y. So now see it, for I can write delta L for steel will be equal to what? Force into L steel divided by area of steel into Young's modulus of steel, right? And similarly delta L for copper will be equal to, this is force multiplied by L copper divided by area of cross section of the copper and multiplied by Young's modulus of copper, right? Simple. And it's mentioned, it's given that this delta L, because extension stretches by same amounts, that means delta L is same, so means this quantity should be equal to this. So then, like, as delta L is same, so this implies I can write F into L steel divided by A steel into Y steel should be equal to force into L copper divided by area of cross section of copper into Young's modulus of copper. And we are asked to find the ratio of what? Young's modulus of steel to that of copper. So this implies Y steel. So we can just take it, F gets cancelled. So this is Y steel divided by Y copper. It's coming out to be what? This L steel divided by area of steel multiplied by area of copper divided by L steel. So this is L steel multiplied by area of copper divided by L copper multiplied by area of steel. This is the ratio, that's what asked, that's what we are supposed to calculate. Let's substitute the values here. So L steel is given as how much? L steel, it's 4.6. Area of copper, it's given as 4 into 10 to the power minus 5. And L copper, it's 4 meter, and area of steel, it's 3 into 10 to the power minus 5. This gone, and this is just wait, let me check it. 4.6 meter, yes, and this is 4 meter. So this is also gone. This is 4.6. Then let me simplify it here. Y steel divided by Y copper. This is coming out to be 46 divided by 30. Just removing the decimal point, and this is equal to 23 divided by 15, and this is the answer. So I hope you should be clear with this problem. Like, things are not complex. Problem appears to be a little bit lengthy and complex. You just need to read it properly, write the data and exactly information given to you, and check the relation, what exactly information is given, what is it is asking, and then get the relation between these two and simplify and substitute. You are getting answers straightforward. So let's see more application based on these concepts. Okay, let's see more application, more problems. So here question example 4. If shear force of, so here F shear is given as 300 Newton is applied on a cube of side. So here we have one cube of side, it's like 40 centimeter, that's 0.4 meter. Find the displacement of the top surface of the cube, the modulus of rigidity. So here, you know, actually when force is applied on the top surface like this, then top surface will displace with respect to bottom by some amount delta x. So that's what exactly it is asking here. So we know actually that eta is equal to F divided by area into shear strain. Shear strain is delta x into L. So we are supposed to get delta x, that is equal to F L divided by A into eta, and everything is given to us. So let's substitute the values. Force is what? It's given as 300 Newton. Length is 0.4 divided by area of cross section. Okay, so this is 40 centimeter is the side because it's cube. So area of cross section, area will be what? It's like 0.4 into 0.4 meter square. So this is 0.16 area, and eta is given as 5 into 10 to the power 10. Right, let's simplify it. So then we are getting it, I can write it 0.4 multiplied by 0.4. So 1 gets cancelled, and this will be like 1 0, and it's like 20, 1 0 also gone, it's like 15. So 15 into 10 to the power how much? Like this will be going 10 to the power minus 10, right? Let me just check it. So this is in meter, and we can write delta x is equal to, that's answer, 15 into 10 to the power minus 10 meter. Nothing here. Force, shear force is given to you, eta is given, everything. This is eta, this is the side, so means side, so we get the area also. 40 centimeter means 0.4 meter. Then eta is equal to force into L divided by area multiplied by delta x. And delta x can be like just rearranged, force L divided by area into, so force 300 Newton, 0.4, and area is 0.4 into 0.4, and this is eta, that is 5 into 10 to the power 10. Just Simplifying it, this 0.4 gets cancelled, this is point, then one more 0, and 4 into 5 it will be 20, 0 gets cancelled, 2, then it will be like 15, and this, yes, 15 and 0 will be left there, so 0, and then you can write it basically 1.5 into 10 to the power minus 8 meters. So this is the displacement of top surface relative to the bottom by this much amounts. You can see it's like straightforward, simple problems are there, not much complex, and just applications. So when the pressure acting on an oil of volume, so volume of the oil is given as volume is 0.5 liter and is increased by this. So now you can see here delta P, that means it's like saying what? It's talking about bulk stress, and here it pressure has changed, increased by this much amount, so directly delta P is given to you. So it's 5 into 10 to the power 5 Pascal. Delta P, the change in volume is 0.3 centimeter cube. Now here you should keep few things in your mind, is that this change in volume is given in centimeter cube and the volume of the oil is given as in liter. So we need to convert both of them in same unit actually. So this 0.5 liter is also equal to 500 centimeter cube, and delta V is equal to 0.3 centimeter cube. So the volume strain is equal to what? 0.3 divided by 500, that is 3 divided by 5000. And delta P is given to you, and now change in volume, to find the bulk modulus. So we know the formula bulk modulus, that is K is equal to what? Delta P divided by epsilon volumetric strain, and delta P is, just substitute the values, it's 5 multiplied by 10 to the power 5 Pascal divided by delta V, 3 divided by 5000. So 3 in this 5000 will be multiplied here. Then we are getting K is equal to, it's 25 divided by 3, so it's 25 divided by 3, and this 3 zeros, so 10 raised to power 8, this is Newton per meter square. You can leave it up to here also, and 25 by 3 also you can simplify one more step forward. So similarly, let's see next problem. A load of 4 kg produces an extension of 2 mm. What it mean actually? So means force is equal to what? 44 into G, that is 40, or like simply 4 into G Newton, and change in length is 2 mm. In a wire of 3 meter length, so length of the wire is given 3 meter, and diameter is also given. So diameter means area of cross section is not given directly, you are given with diameter 1 mm. In diameter, calculate Young's modulus of the material. So here also everything is provided to you. So what will be the area? Area will be like pi into d square by 4, that is pi into d is 1 square into 10 to the power. If I am converting everything in SI unit, then it will be like minus 6 divided by 4. So it's pi by 4 into 10 to the power minus 6 meter square is the area, and delta L is equal to 2 into 10 to the power minus 3 meter. And now what is Young's modulus? Young's modulus is equal to force divided by area multiplied by delta L into L. Let's substitute everything here. So force is equal to 4 into G, 10 multiplied by L, that is L is given as 3 meter, divided by area, area is pi multiplied by 4 into 10 to the power minus 6, and delta L, that is equal to 2 into 10 to the power minus 3. Let's simplify it. So we are getting it 2, then it's 2 left, and this pi and 10 to the power 3, like 6 and 3, 9 and 10, so this is 12 into 2, 24 divided by pi multiplied by 10 raised into 10 raised to power 9, and this combining, so I can write it's 24 by pi into 10 raised to power 10 Newton per meter square. This is also enough. You can simplify one more step also. So this is the Young's modulus of wire. So things are not complex, you should remember the formula just and see the application how we are doing. Like read the problem carefully, get the information from the question, and try to get the relation and just rearrange it what is given and what is asking. Like so rearrange for that, substitute the values, you will be getting straightforward answer. So this is all about application of the concept that we have just studied. let's continue from here onward in the next class. Thank you.